Here we're going to talk about annuities. We're going to actually talk about future value annuities. And so I don't want you to get too lost in this part, but there's something called an annuity due, and we're not going to talk about that. There's another annuity called an ordinary annuity, and that's what we're going to talk about. See, annuities, when you have an annuities, like if you're making multiple payments on something, you could have your first payment made at the beginning of the first period or at the end of the first period. So we're going to focus only on ordinary annuities, and that's where you make your payment at the end of the first period. So whatever the period is, whether it's months, quarters, years, the payment will be made. First payment will be made at the end of the first period. Now, there's two types of ordinary annuities that we're going to talk about. Now, in this section, I'm going to focus on future value annuities. But in the next section, I'll focus on present value annuities. And at some point, I promise you, you're going to ask yourself, how do I know whether I use a future value formula or present value formula? And the patented answer I give for this are, first of all, are the payments designed to increase the balance or designed to decrease the balance? If the payments are designed to increase the balance, you have a future value annuity. If the payments are designed to decrease the balance, you have a present value annuity. So again, you can freeze the video and look at these, but the ones on the left are future value annuity problems, and the one on the right are present value annuity problems. And I'll just summarize here. In this example, you're actually making monthly investments of $500 a month into an account. So in this example, the monthly payments are designed to increase your balance. But over here, Sharon's making car payments, and when you're making car payments, in other words, when you're trying to pay something off, your monthly payments are actually designed to decrease the balance. So this one would be an example of a present value. Here, Juan is saving for a new computer, so he's investing money in an investment institution, and obviously as he invests his money, it's going to increase the balance in his account, so it will grow to, what he needs it to grow to. It looks like $1,500. So this would be a future value annuity problem. But over here, you actually start with $10,000 in a trust fund, and then you actually, how much are the quarterly payments? So you're going to be paid out of that trust fund quarterly payments. So the question is, how much are the quarterly payments? In other words, how much can you withdraw from that fund each period? Well, when you take money out of this trust fund, the balance of this trust fund is supposed to decrease in value. So therefore, when you take money out and it decreases the value, then that would be an example of a present value annuity. Now, I'm going to go ahead and develop the future value annuity formula, but if you don't follow this, don't get too worried, because just like before, the development of it is not near as important as actually being able to use it. So we'll learn how to use the formula later, but let me show you how you can develop this. Let's start with this example. Suppose you want to make quarterly deposits of $2,000 into an account that earns an annual interest rate of 6% for a period of 2 years. How much will be in the account at the end of the 2 years? Now, so you're going to put $2,000 each quarter over a period of 2 years, or 8 quarters. All right, so if you put $2,000 into the account for 8 quarters, that would give you a total of $16,000. But we're going to find out that this account will have more than $16,000 in it, because each one of those $2,000 deposits that you make are going to earn interest. Well, I'd say each one. The last one won't, but the rest of them will. Okay, let's review some facts here. First of all, the quarterly payment, which we'll call PMT, is $2,000. And the annual rate, R, is given to be 6%, or 0.06. the compounding schedule is quarterly, so we know M is 4, and the number of years T is 2. So from this we know that I is, since I is just the rate divided by M, then I would be 0.06 over 4, which is 0.015. And since N is just the number of compounding periods per year times the number of years, N would be 4 times 2, which is 8. Now, we could calculate each one of these payments separately. So let's start with the last payment. The last payment, that's your 8th payment. That payment is only going to be worth $2,000. And the reason it's only going to be worth $2,000 is because it went through 0 compounding periods, because you make that payment at the end of the 8th period. And remember, that's when we want to count our money. So that last $2,000 payment is only going to be worth $2,000. Now, what about the 7th payment? Well, the 7th payment is going to go through 1 compounding period. So if you calculate what it's worth after 1 compounding period, it's going to be worth $2,030. Now, the 6th payment is going to go through 2 compounding periods. So if you apply the formula, the compound interest formula, that we get 2,000 times 1 plus I to the 2nd power, which is 2,060.45. And then the 5th payment is going to go through 3 compounding periods, and so you would have 2,000 times 1.015 to the 3rd power, and that gives me 2,091.36. And you can kind of see where this is going. And so each one of these is going to go through more and more compounding periods, so therefore they're going to actually earn more and more money. So notice your first payment, the one you made at the very beginning, it's going to actually earn over $200 in interest, but notice your next to the last payment only earned $30 in interest because it didn't go through, it only went through 1 compounding period. All right, so what I did here is I showed you how each payment grows, how each one of those 8 payments grows. But if the first payment grows to this amount, and the 2nd payment grows to this amount, and the 3rd payment grows to this amount, and the 4th grows to this, 5th grows to this, the 6th grows to this, the 7th grows to this, and of course the 8th stays as this amount, then you can now figure out how much all of these are worth. And so if you add all of these up, you'll get the future value of this annuity by adding it up. Well, we obviously don't want to have to do this. We don't want to have to do it this way. Because what if I did this instead of for 2 years? What if I did it for 20 years? Then I'd have to do 80 of these. Okay? And I don't want to do 80 of these. So there's got to be a better way to solve this problem. Well, let me show you how we get the formula. Now, notice that to get the future value, all I did up here, when I got up here, when I added all these up, if you think about it, all I added up was I added up the 2,000 times 1 plus I to the first, 2,000 times 1 plus I to the second, 2,000 times 1 plus I to the third, all the way up to 2,000 times 1 plus I to the 7th power. And now I'm going to do a little trick. I'm going to multiply both sides by 1 plus I. Now when I say I, I'm saying 0.015 is I. So multiply each term of this equation by 1.015. So if I multiply the left by 1.015, that'll give me the future value times 1.015. If you multiply each one of these by 1.015, it just gives me another power of 1.015. So 2,000 times 1.015 is just 2,000 times 1.015. 2,000 times 1.015 times 1.015 would be 2,000 times 1.015 to the 2nd power. 2,000 times 1.015 squared would be 2,000 times 1.015 to the 3rd power, and so forth. And so this 2,000 times 1.015 to the 7th would be 2,000 times 1.015 to the 8th. Okay, don't worry, it's going to simplify here. Now, let's take the top equation. Let's subtract the top equation from the bottom equation. So here's the bottom equation, and here's the top equation. Now let's subtract these. Now on the left-hand side, I'll just get this minus this. So I get future value. I get 1.015 times future value minus future value. Well, if you take 1.015 minus future value, that's just going to give you 0.015 times future value. Okay? Now, but what do we get on the right-hand side? On the right-hand side, if you subtract, well, this would cancel with this term, this would cancel with this term, and the terms in the middle here are going to cancel, all right? And then this term cancels with this term. So all the terms cancel except on the top, you're left with this term, and on the bottom, you subtracted, you were left with this term. So what we get on the right would be we get 2,000 times 1.015 to the 8th minus 2,000. And if I factor 2,000 out of these two terms, I get 2,000 times 1.015 to the 8th minus 1. So now put it together. On the left, I got 0.015 times future value. On the right, I get 2,000 times this. Now if I divide both sides by 0.015, I get a formula for future value. And that formula is just 2,000 times 1.015 to the 8th minus 1 all over 0.015. Now what's interesting though is this 2,000 is just your payment. The 0.015 is just I, and 8 is just the N. So really it looks like this formula is just based on the payment, the I, and the N. And actually it is. The formula is actually to find the future value of an annuity. The formula is you simply take the payment, just like I did up here where I took the 2,000, and then you multiply it by this fraction where the numerator is 1 plus 0.015. So that would, what's the 1.015? That's just 1 plus I. And then the 8 was the N. So I have 1 plus I to the N minus 1. And then all divided by I. So to make a long story short, the formula for finding the future value of an ordinary annuity is equal to the payment that you're making, the multiple payment that you're making, multiplied by 1 plus I to the N minus 1 all over I. And we've already talked about what all these variables represent except for the future value and the payment. And hopefully you know the future value is just the sum of all those payments plus the interest. And then the payment is just the payment that you're making, whatever payment it is. Okay? And so that's the formula, development of the formula for the future value of an annuity. And I guess I should say something about this down here. I don't do these in this class, but these strange looking symbols you might see, these are used for looking up values in a table. Like you can actually look up in a table, like here, you can find a value for this fraction by just looking up the value that corresponds to an I value of 0.015 and an N value of 8. And that way when you look it up in the table, you just multiply the 2,000 by what that number is in the table. But we're not going to do it with tables. We're actually going to do it with using the actual formulas. So I'll show you some more examples in the next video, but real quick, let me go ahead and show you if you took this formula and solved it for payment instead of future value, you would actually get another formula which is called the sinking fund formula. So this formula is a sinking fund formula. So this formula would be if you knew what the future value you wanted, like let's say you knew you wanted to have $1 million at retirement and you wanted to know what monthly payment would get you $1 million, then you could use this formula. Whereas this formula up here will tell me, if I know what my monthly payment is, it'll tell me what the future value would be after a certain time period. Okay, that was a little longer than I meant for it to be, but anyway, that's the development of the future value annuity formulas, and we'll work examples in the next video.